Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into an 8th grade topic, rational numbers. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below. So use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what we see today, or even on homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I've been linking my 8th grade playlist in which I cover a lot more topics. So if you're interested in that, make sure you stay tuned. This video is going to have 3 parts, so leave a like, smash subscribe, and let's get started. So to begin this video, let's first define what a rational number is. A rational number is going to be any number in which you can write it as a fraction or a quotient of 2 integers. Once again, a rational number is going to be any number in which you can write it as a fraction or a quotient of 2 integers. That just means that if you have a number A, right? A is going to be some number. If you can do this, in which A equals some B and C, and we know that B is an integer and C is an integer. Now it's important that C is also not 0 because we're not trying to blow anything up. It has to be defined, but we know that this and this to be true. Both of these are integers, then A is going to be rational. So by definition, we already know one group of numbers which automatically have to be rational numbers, and that's going to be all of our integers. Our integers have to be rational numbers. So I'm just going to put 1 here as a denotation of all the integers. We know that this has to be a rational number because it can always be itself over 1. That's your fraction. That's your quotient. Those are your 2 integers. Any integer. 1, it could be 12, it could be negative 12. It doesn't matter whether you're positive or negative. As long as you're an integer, you can write yourself over 1 to give you your quotient, and therefore you will be a rational number. We also have some decimals that are also going to be considered rational numbers. Let's say we have something like this. Let's say 8.032. This right here is an example of a decimal that is a rational number. This is a finite decimal. Finite because it does not continue. It's only 3 decimal places. This is going to be a rational number because you can always write your finite decimals as a fraction. Therefore, they're going to be rational numbers. But what about some decimals that aren't so finite? Let's say we have something like 0.3 repeated, right? 0.3 repeated. Now this is going to be a repeated decimal. We know that this doesn't end. This is going to be 0.333 continuing. You're just going to repeat that 3 forever and ever. This is definitely not a finite decimal. Is this going to be a rational number? Yes. This is going to be a rational number because we know that you can always write your repeated decimals as fractions as well. And because you can do that, they're going to be rational numbers. And it doesn't matter if you're a mix or a pure. So the mixed ones are going to be something like this, where you have points, let's say 8, 3, 5, and 3, 5 is going to be repeated. This is not a pure repeated decimal because this doesn't repeat, but it has a portion that is repeating. It doesn't matter how you look. Both of these can be written as fractions. So both of these will be considered rational numbers. And since we're talking about rational numbers, let's not forget our perfect radicals. Now, you know your square root of 4, but it doesn't have to be just square roots. You can have cube roots as well, as long as it's a perfect radical. So whether it be square root of 4 or let's say the cube root of 8, these are going to be rational numbers. And why is that? Well, any perfect radical can be reduced to an integer. And we already said that all integers are going to be rational numbers. The square root of 4, 2. Cube root of 8, 2. So if you can reduce this to an integer, you're going to be a rational number. So now that we've talked about rational numbers, let's talk about some numbers that aren't so rational. Now you may have already guessed it, that your irrational numbers are going to be all the numbers that aren't rational. However, let's say you want a more formal definition. Well, that's just going to be any number that you cannot write it as a quotient of two integers. If you cannot write that number as a quotient of two integers, it is not a rational number. It has to be an irrational number. And I bet you've already run into irrational numbers without even realizing it. If you've seen this before, this is an irrational number. Pi is an irrational number. Let's say you run into this before. If you're dealing with exponentials, let's say it was something like e to the x, right? Well, the base, the e portion, is going to be an irrational number. If you were to look up what these values are, they are going to be something that is infinite, yet not repeating. Both of these go on forever. They're going to be decimals that go on forever. However, unlike the repeating decimals that we talked about, these are not repeating. That's the characteristic of these two numbers. And by extension, your irrational numbers will have that same characteristic. So along with the definition, you cannot write it as a quotient of two integers. If you're trying to convert it into decimal form, it will be a non-finite, non-repeating decimal. It will go on forever and ever and ever and will not repeat. So another example of an irrational number is going to be your non-perfect radicals, your square root of 2, your cube root of 5. Any number that when you convert it to a decimal is non-finite and non-repeating, or following the definition, you cannot write it as a quotient of two integers, will be an irrational number. So let's move on to a couple of examples to really drive this point home. So here we have a couple of examples in which we're trying to figure out, is it rational or is it going to be irrational? So we're going to simply write an R for rational or an I for irrational. So our very first example, is it going to be rational or irrational? We have pi over 2. Well, this is going to be irrational. You have that pi, and simply dividing it by 2 is not going to make it rational. Pi is irrational, and if you're going to multiply it by a rational number, you're still going to get an irrational number. That's something we can talk about a little bit later, but whenever you have an irrational number and you multiply it or divide it by a rational one, you're still going to result in an irrational number. That's what's happening here. So this is going to be I for irrational. How about number 2? Is this going to be rational or irrational? This is going to be rational. Don't get caught up in the fact that you have a couple of numbers here that aren't repeating. This whole thing is going to ultimately be a repeating decimal. And we said that all repeating decimals are rational because you can always write them as a fraction. So if you need that refresher on how to do just that, check out my video. You can find it right up here. I give you a couple methods that are going to be pretty easy to understand on how you can convert all of your repeating decimals into fractions. Let's move on to our third example. Here we have something in scientific notation. This is simply going to be a whole number when you expand it out. That is going to be an integer. That's going to be a rational number. All of our integers are rational numbers. How about number 4? We have square root of 2 over square root of 8. Now, you have to do a little bit of math here, but if we were to simplify this, you would see that all of your radicals fall out. They cancel out with each other, and you're left with a fraction. Therefore, that fraction is going to have no radicals, just integers, making this a rational number. Do the math. You'll see it for yourself. But all of these are going to cancel out their radicals, and you're going to be left with a fraction without radicals. How about our fifth one? We have negative 8 over 50. Well, this is going to be another rational number because you have two integers. It doesn't matter if you have it negative or positive. That doesn't change anything. This is a quotient of two integers. Therefore, it's a rational number. How about our last one? We have square root of 16 over square root of 2. Is it going to be rational or irrational? Well, once again, you have to do a little bit of math here. But if you were to simplify this, you would see that not all of the radicals go away. And it's not going to be a perfect radical that remains since it didn't go away, thus making this an irrational number. So these are just a few examples to kind of drive home which numbers will be irrational and which ones will be rational. So I hope you were able to follow along with today's video, and I hope you now know which numbers are going to be rational and which ones are going to be irrational. However, if you have any questions about what we saw today or even your own homework, remember you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. And if you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found the video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share the video with a friend. Well, that's all the time I have for today. I'm really hoping to help with your homework, and I'm looking forward to see you again next week. I'm Courtney, here's your playlist, and this has been another session of Tutor Me Sempai.